were not present, what we were discussing is what is this thermal design subject. Okay. So I actually mentioned that thermal design, even though it's the name of the course, but what we will do is thermal design plus also optimization of designs. Okay. So we are now trying to understand what this subject is all about. So we are starting with an example. So there is a DG set, and the DG set gives out flue gases, obviously, okay, because there is burning of diesel and all that. So that the flue gases carry some heat which is actually useful. So that heat can be utilized. So how do you utilize that? In the example that we were considering in the last class, that heat is utilized to convert some water to steam. Why? Because maybe where the DG set is, there at that place we also have a requirement of steam for some other process. Okay, maybe you want to use that steam to dry some fabrics, just as an example. You know, textile industry uses steam to dry fabrics, things like that. There can be many other applications of steam. So we need a heat exchanger for that, which will transfer the heat from the flue gases to water. And there are many types of heat exchanger which are possible, but we thought, based on experience, we thought that we will start with a finned tube heat exchanger. Okay, so what is a finned tube heat exchanger? It kind of looks like this. So there are some tubes and there are some fins. So we will flow water in these tubes and we'll have fins on the outside. So the fins will be on the gas side, because on the gas side the heat transfer coefficient is low. I think you all know that, right? If you have a liquid flowing, then the heat transfer coefficient is higher. If you have gas flowing, then the heat transfer coefficient is lower. Okay. Now we place these tubes along with the fins. So these tubes which you see in this figure, they also have fins, but this is only a schematic, it doesn't show all the details. So you cannot see the fins, but these fin tubes are placed in a duct. Okay, so what you have is the flue gas from DG set coming and flowing over this tube bank. Okay, so the terminology that we use is tube bank. Okay, this bank of tubes. Now we did some design, actually more like based on experience we chose a few things, like we chose a tube base diameter, we chose a ID of 14 mm, then fins of 2 millimeter height, spaced on the tube with a pitch of 4 mm. These things, how do we get these things? These things are based on previous experience and good industrial practices. Okay, so that means that there are engineers in your company who have used fin tube heat exchanger for maybe similar kind of applications. So they say that okay, maybe this sort of configuration should work. Okay, then we start with this. Now in any design process, of course, if this doesn't work, we can change it, right? That you know. You have done machine design, and in undergraduate you have done maybe 1 or 2 courses on machine design. So you know that you start with something and if necessary you change that also. So these are the choices that we are going with. Now here, apart from the tube diameter, tube inside diameter, tube base diameter, then the fin dimensions, fin pitch, we also have to say something about the spacing of the tubes. Okay, so the spacing is determined by 2 things. There is this ST, which is the transverse spacing between the transverse pitch between the tubes, and this is a longitudinal pitch. Okay. Now this is one arrangement which we call a staggered arrangement. Why staggered? Because the flow comes like this, and then the flow will not pass, doesn't have an opportunity to pass straight through because it's obstructed by these tubes. So we are saying that there can be a staggered arrangement, and staggered arrangement is the one which you see on the screen, but inline arrangement will mean something like this. Okay, this is inline arrangement. So in inline arrangement, the flow kind of has a tendency to bypass the tubes, which can affect the heat transfer. Okay, so we can decide ST and SL. Now, again, this is only an introductory discussion. So we are actually not designing anything. Okay, I'm giving you an overview of what sort of things we will do in this course. So again, based on experience, we choose ST and SL to be 32 mm and 30 mm. And we also have to choose the size of the duct in which these tubes are placed. Okay, and the duct dimensions have to be such that the gas side velocity is all right. Okay, so the duct dimensions, by that we mean transverse dimension as well as the length, longitudinal dimension. So the dimensions have to be such that, okay, if you're thinking about so many tubes, it should be able to accommodate all the tubes, right? Can you close? Yeah, so as you can see, the course is being recorded, so doors should be closed all the time. When you come in, please close the door. Right. Uh, so we'll have to be able to have sufficient length where we can sufficient this dimension so that we can place all the tubes, right? And if this duct transverse dimension becomes very large, of course the velocity of the gas will become very low, right? Which is not desirable, isn't it? Because ultimately, what do you want? You want sufficient velocity so that there is heat transfer, isn't it? Uh, if you if in your room you decrease the speed of the fan, of course the heat transfer comes down. It's something like that. Okay, you want sufficient velocity. Now, let's say the gas velocity over the tube bundle is 10 meter per second. Okay, and this is the gas velocity, and the water velocity, let's say, is about 1.5 meter per second. Again, these are chosen from experience. Now, usually the water velocity is limited to 3 meter per second to minimize erosion. Because if you have water velocity which is too high, then the tube inside surface can get eroded. Okay, so these are the kind of considerations that you have. And we also have to decide on the number of tubes that are needed in a single pass of the heat exchanger to achieve the required mass flow rate of water. Okay, so water is flowing and this is gas flowing. So the water flow has to be divided into sufficient number of tubes, and all the tubes together should be able to give you this kind of velocity in the tube. So again, we don't want the water velocity to low. We don't want the water velocity too high because that can cause erosion. And what do we do after this? We can calculate the heat transfer coefficient on the gas side and also on the water side. How? The way you used to do this in your undergraduate heat transfer, because you used to calculate heat transfer coefficient with the help of various correlations, isn't it? Now the correlations here will change. Why? Because it's not a simple geometry. The kind of geometry that you are more used to is like flow over a flat plate, or flow inside a pipe, okay, or maybe at most flow past a pipe, or flow past a sphere. These are things that you might have seen. But here the flow is a bit different because it's like a bank of tubes in a duct, okay? And especially the gas flow outside the tube is not something which you have studied previously. Flow inside the tube, that is the flow of water that you see inside the tube, that is still something that you're familiar with, right? That you have seen in the discussion of internal flow when you were studying undergraduate heat transfer. Okay, you can recall what you studied here, and you have Nusselt number correlation and things like that. For laminar flow, for turbulent flow, those can be used to get H on the inside. Okay. Now, uh, once you get the heat transfer coefficient on the uh, inside, which can be HI, okay, and you get heat transfer coefficient on the outside, which is HO, these can be combined to give you an overall heat transfer coefficient. Okay, an overall heat transfer coefficient. And so this comes from some correlation. This also comes from some correlation. So you can get the overall heat transfer coefficient. You can also calculate an effective mean temperature difference. Okay, so there is some flue gas which is coming at a particular temperature. Do you know the temperature? Yes, because it's coming out from the DG, so you can measure that, and that is part of the requirement, right? And you know that temperature, and water temperature, water is available in the plant, right? So you have water at some temperature, maybe I think we said in the last class 10 degrees Celsius. So just as an example. And then that water, you wanted to convert that to, for those of you who came in the last class, 2-bar saturated liquid, right? This is what we, sorry, saturated steam. That's what we discussed. So you can calculate the heat transfer which is required to take the water from the 10 degrees Celsius to saturated vapor stage. And using that, you can also calculate what is the change in temperature of the flue gas, right? Because the flue gas entry temperature you know, and you know the flow rates of both these, isn't it? So you can do an energy balance and get all the temperatures. And once you have all the temperatures, then you can also calculate some mean temperature difference, isn't it? Like you know LMTD, isn't it? LMTD you must have studied, log mean temperature difference, but here calculations will be a little bit different because of the complicated geometry that we have. Okay, and so we got an effective mean temperature difference between the two streams. We also got an overall heat transfer coefficient. So then based on this, see, it's like UA multiplied by an effective temperature difference. Okay, so UA and some delta T effective, this will give you what? Heat transfer, right? So the heat transfer you know. And so based on that, you can get the area. And once you get the area, then the length of the heat exchangers tubes can also be calculated. See, we took the tube dimensions, like tube diameter that I mentioned. Diameter was chosen from experience. So if you know the area, then you can also choose the length, because the length multiplied by the pi d, that will give you an area of a tube and then the number of tubes and all that. Okay, so with all this, you have basically you have a design of the heat exchanger. Okay, we didn't do any calculation, but broadly we understand that this is the process that we can follow. You know, get HI, HO, get overall heat transfer coefficient, get all the temperatures, and then from that get the area, distribute that area in terms of the number of tubes. Okay, so you can get a design. So this design will likely work unless you made mistakes. Okay, so this design will give you if you make the heat exchanger with that design, it will give you the required amount of steam. That is the idea. Fine. So this is part of what we are doing in this course. Heat exchanger is one topic which we'll do in some detail. Okay, but we will cover other topics also. As I mentioned in the last class, we'll do heat sink, we'll do heat pipe, and then we'll do some modeling, simulation, and also optimization. Okay. Now here, the design that we have just now seen, okay, if I give this problem to all of you individually, right, then your design will not be the same as his design, isn't it? Because you might uh, make different choices when it comes to the tube diameter and the gas velocity and the water velocity, the number of tubes, the duct dimensions. It becomes some kind of subjective, right? It's not like there's a fixed thing that all of you, if I don't, if you do the design individually, you will choose different things. That's natural, right? And if you're doing the calculations correctly, then and if you're not making some strange assumptions, those designs will work. They will still all give steam, right? So we have multiple designs which are okay, but then uh, we don't know whether your design is better than his design. We don't know that. Okay. So um, we will have to do some kind of an optimization to choose a design which is the best amongst many possible feasible designs. So how do we do this optimization? So optimization will cover in the latter part of the course, okay, after the mid semester. So the optimization will be subject to some kind of maybe constraint that you have to follow these things within these limits. The design has to be done, and also we need an optimization criterion. So the criterion, as I discussed in the last class, criterion can mean maybe the minimization of the initial cost. Okay, so there are multiple designs, whichever gives a minimum cost, that's a better design. That's the thinking, right? Or it can be the pressure drop on the gas side. It can be the pressure drop on the gas side, that um, you don't want too much pressure drop on the gas side, because the this heat exchanger is downstream of the DG set, right? So if the heat exchanger causes a lot of pressure drop, then the DG performance will deteriorate, right? Because it's part of the circuit. So you want to lower the pressure drop on the gas side. Um, so these can be possible choices of the optimization criterion. You may say that, okay, I want to minimize the cost. I want to minimize the pressure drop, things like that. Based on these, the design which performs the best, that's an optimized design amongst possible designs. Okay, so the cost, let's say we talk about cost as an example, just as an example. So the cost of the part of the cost of the steam produced can be part of an objective function, plus the effect of reduction in DG set output caused by the gas side pressure drop. Okay. So we are thinking about the cost. One is that to produce the steam, there is some cost which is required because you're including the heat exchanger and all that. The other part is that, okay, the DG output will also get affected because of the pressure drop due to the heat exchanger. And these can be combined along with the initial cost of the heat exchanger. Along with the initial cost of the heat exchanger. Okay. So cost is of two types, as you know. Cost is, it's got an initial cost and also a recurring cost. What is the initial cost? Initial cost is like for making the heat exchanger, you incur some cost, right? So that's the initial cost. So that's a capital cost. What is recurring cost? Recurring cost has to do with the pumping cost. Okay. So here there's some pressure drop which is needs to be overcome uh, to push the gases into the heat exchanger, and you have to pump the water also. So these things are recurring costs, right? So you develop a composite cost function which has a initial cost and a recurring cost, okay, and then you try to minimize that for all the designs. The other option is that, okay, you just look at the profit and then heat exchanger design which maximizes the profit. That is also called optimum design. So there are other options also. Let me skip this particular point. So the number of feasible designs is extremely large. So we need a strategy to arrive at the optimum design. And this requires some optimization techniques. So this requires some mathematical techniques. So you can write equations and you can optimize these. Okay. Some optimization you learned in industrial engineering course in undergraduate. Okay. Maybe you know something, but we will do other techniques and we will also make sure that we apply those techniques to thermal engineering problems. Okay. And that optimization can be mathematical, you know, just based on some equations and all that, but it can also be numerical optimization. Okay. So sometimes mathematical optimization is not possible, so you have to do some numerical optimization. Okay, so this requires, before you optimize, you require some solutions and some variations in the solution based on some simulation procedures. So there are some system simulation procedures also. Again, so what does simulation mean? You have a system, let's say a heat exchanger. For that you write some equations, you know, things like pressure, expression for pressure drop, expression for HI, expression for HO, expression for U, expression for the area calculated, things like that. You can have a code which has got all these expressions. Then you can actually uh, vary some of the input quantities and then see what is the effect on the output quantities. Or there can be other systems where you have to write differential equations, either ordinary differential equations or partial differential equations, and then you solve them. So that's basically simulation. Okay? And then those simulations can be utilized to predict the performance of each component of the system. And then a system has multiple components, and then you put the performance of each individual component to get a system, total system performance. Okay, and then that helps in the whole optimization process. Okay. So the other point is that we can, once you have a simulation procedure, you can vary various inputs and then see the effect of those variations on the performance. So let's say for a heat exchanger, you have a simulation code. So what can you do then? You can change the flow rate, you can change the temperatures, you can change various dimensions and see how the heat exchanger performs based on these variations. Okay, so the importance of simulation is that it will help you understand the system meaning the heat exchanger in this example, better. Okay, so you get a feel for this and you can quantify the performance. And then the other thing to remember here is that for any system, there is some design operating point. Okay, so and the manufacturer will tell you that this is the operating point at which the system will perform the best. Okay, so they made a system and that operates the best. You know, it's actually designed for this kind of condition. But in reality, the system will have to operate at other conditions also. So there is design conditions, but there are also system will also operate at off design conditions. Okay, so let's say there is a turbine, let's say there is an IC engine, whatever. These they have some design points, some generator also. Let's say they have some design points, but they also work off design. Okay, you cannot have a system which will always work at the design point. So it will have to cover a range of load range. Let's say there's a car, so it has to face a range of loads. It has to use a range of speeds. Okay, various things. So off design performance is also important. So once you have a simulation program, you can do a parametric study, change various things, and see its performance at the design condition, but also at off design conditions. And this whole exercise can help you develop control strategies also. So if it is going like, if it's performing too poorly, if you have a simulation code which tells you what is the performance at various input parameters, then the performance can be tweaked back, the input can be tweaked to go closer to the design point. Okay, so these are this is like, I'm saying these things broadly, but we will see these in more detail when we actually start doing the course topic wise. Okay, so we'll do heat exchangers, heat pipe, heat sink, but then we'll go to simulation, then we'll go to modeling, we'll go to simulation, then we'll go to optimization. When we cover each of these topics in detail, you will understand these in greater detail. Now, this we just looked at the heat exchanger example, but let's also do some other examples. Again, broadly, without actually doing any calculation. So this is an example of cooling of an electronic component. So let's say that there is a circuit board, okay, with electronic component, and you want to cool this. Why? Because if the electronic component gets overheated, it will not perform properly. It might fail also. So a couple of things are important. It can get overheated, or if it gets, even if it doesn't get overheated, if its temperature rises quickly for some duration, some small duration, that is also not desirable. Okay. So you want to cool it. Now there are various cooling strategies. So for example, you know, desktop computer, it has got a fan which will cool and things like that. There are other cooling strategies also, which will come to a little later. Now, the first thing to understand is that if I give you the dimensions of the circuit board, dimensions of the electronic component, all material information, and the heat dissipation rate from here, and if I also tell you the fan capacity, right, then you can solve this problem. Okay. Problem meaning what? You can write governing equations and solve those to say what will be the temperature distribution here, or maybe the temperature distribution here, what will be the velocity profile of air around the component. You can get everything, right? So this is the sort of thing which you have seen in convective heat transfer. In convective heat transfer, you didn't have maybe a component like this. Maybe it was just flow over a flat plate, right? This is a more complicated version, a more difficult version of external flow, right? If this is your flat plate and the flow just goes over this, and let's say this is heated, you know how to solve this, isn't it? You have done in undergraduate. The flow problem is solved by Blasier's method, and the heat transfer problem is like a follow-up of the Blasier's method where you add the energy equation also. Okay, so it can be solved. So you need governing equations, you need boundary conditions, you can solve this. Now here also you can solve this, it's just that it's going to be more difficult. Again, you write conservation equations. What are conservation equations? Mass conservation, momentum conservation, energy conservation. You need boundary conditions. What boundary conditions? You know, non-slip on the no slip conditions of the surface, and then maybe a heat flux condition which tells you how much heat is going into the domain, like that. So it can be solved. Okay. Now, if you solve it and if you solve it, are you going to get the same solution? In this case, the heat exchanger example, I told you that different people are going to get different things. But here, same. Provided, of course, you don't make mistakes and all that. If I give you all data, all material data, all heat dissipation data, fan data, if you do this correctly, you're going to get the same solution, right? If you, of course, it may be you have to make some assumptions like constant thermal conductivity and all that, but let's say you make those assumptions, then you're going to get the same solution, right? So this is an analysis problem. What I just now described is an analysis problem. So in other courses, fluid mechanics and heat transfer, what you had actually done was that the problem was given, flow over a flat plate. You solve this, you get a solution, that's it, finished, fine? So that's an analysis problem. The solution is unique for the given geometry, material properties, and dimension. The solution is unique, it doesn't vary from one person to another. Okay. Maybe the mathematical method of solution can vary a little bit. I mean, if maybe there's some problem, you use separation of variables and somebody else uses method of Laplace transform, whatever. Okay, there are other methods also. But it's going to be the same solution. Okay, now what is the design problem? Okay, for this case, what do you think will be a design problem? I just described the analysis problem. What is a design problem? Just think about it. So here's a question I'm asking you again. Suppose somebody says you design this system. And what is the meaning of that? What are you expected to do? Better performance, okay? So better performance will mean what? What is better performance? In this context, in the problem that I described, what is better? Heat dissipation should be more. Okay. Correct. But what we try to do is, see, you don't want to bring in the most powerful fan here to lower the temperature to very low levels. Okay. That might not be required. What is important is that if somebody tells you from experience and from some knowledge of electronics that this works up to 80 degrees Celsius, just as an example. Okay, then the design problem is that you choose the fan and maybe choose some dimensions also. Here mostly fan only in the simple problem, that you make sure that the temperature is less than 80 degrees Celsius for the heat dissipation from this component which is given to you. The electronics person who is working on this will give you the heat dissipation from here, so many watts. These are like small components, isn't it? So you have to make sure that it's less than 80 degrees Celsius. If you can do that, then your job is done. But then also, since it's a design problem, less than 80 degrees Celsius can be achieved by some of you with different choices of materials and fans and dimensions and all that, right? So there also there can be variability. Okay, so there what should we look at? We should look at the optimum design situation and choose the one which maybe gives you the minimum cost or something like that. Okay, as long as it meets less than 80 degrees Celsius. See, if it's less 80, if up to 80 degrees Celsius, it works fine, then we will not like to reduce it to 50 degrees Celsius, because that is like an overkill. You know, that's like unnecessarily doing too much. Because if you try to bring it to 50 degrees Celsius, then you will spend more money. Okay, then you will need more power here, and you will spend more money, right? Maybe it will become more noisy also if you run it at a higher capacity. Okay. So this is a design problem. The first one was an analysis problem, which has a unique solution, but the next one is a design problem. Okay, so there is a component temperature. Component temperature is TC, all right? And it has to be kept below T max, let's say 80 degrees Celsius. Then you just make sure that TC is less than T max. So this problem is open-ended, right? Actually, if we relax these things a little bit, we can say that, okay, we maybe you don't use just a fan. Maybe we can use something else, which is actually a heat pipe. Okay, now heat pipe is something which is extensively used in laptops, for example. And we will discuss this in detail. We'll have maybe 4 or 5 lectures on heat pipes. So this is an interesting technology which is relatively new. Okay? Actually, it has been around for quite some time, but compared to maybe heat exchangers, it's new, definitely. So if you open a laptop, you can actually see a heat pipe. Did anybody hear about heat pipe here? You heard about heat pipe. In what context? Okay. 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 Yeah. So when we go to heat pipes, I'll show you some photographs of heat pipes in laptops and all that. Okay. So in a heat pipe, what happens is that phase change is used. Okay. There's some liquid in the heat pipe, and the liquid picks up heat from the hot component, and then it evaporates, then it goes somewhere else, and there it condenses, thereby releasing that heat. Okay? So in the previous schematic that we had, it's actually suggesting that you can use a heat pipe. You need not use a heat pipe, but you can also use a heat pipe if there is a need. So the heat pipe will collect heat from here. So there's a liquid inside the heat pipe which will evaporate. How will it evaporate? Because it will pick up the heat from here, from the electronic component. And then that vapor of that liquid, okay, so that will move to the other part of the heat pipe, where it will condense, thereby it will release the heat. So it's continuously picking up heat from one place and releasing it somewhere else. So that is also a cooling mechanism. So this is called conceptual design. So the conceptual design can be just a fan, or the conceptual design can be just a heat pipe, or the conceptual design actually should be heat pipe plus fan, where typically you like to maybe also use the fan around here to help the cooling. Yeah. So whatever it is, that's a conceptual design. Then there is some calculations, etc. Right. So that sort of thing we'll do later. And let's take another example. So this is another example. This is an example of molten metal solidification. So this you can see, this is an insulation. This one is an insulation. Okay. This one is the mold, right? And in that you pour molten metal, so the molten metal will solidify. So this is a production engineering problem that we know, but one interesting thing about production processes is that even though we say that that is production engineering, this is thermal engineering, obviously there is a lot of thermal engineering in production also, right? So the molten metal will start solidifying. So this part will solidify first, right? Then the central part is more like molten, right? And so this is kind of molten metal. This is solidified metal, and between them you have a zone which is kind of a mix of molten metal and solid, and which is progressively getting solidified. Okay. Now here again, if I give you the details, like the dimensions of this system, dimensions of the insulation, the material of the insulation, the metal properties, etc. So metal at what, molten metal, which molten metal, etc. If I tell you all these, then and I'll also give you maybe the heat transfer coefficient at the outer surface of the mold, okay, and some insulation properties. So if all these material properties and all specifications are given properly to you, then you will be able to solve this problem and get again a unique solution, right? In the last problem, cooling of electronic component, you agreed that you are going to get a unique solution. Here also you are going to get a unique solution if all details are given to you, correct? So this is again an analysis problem. This is not a design problem, because once all details are given, you write the conservation equation. So here it can be uh, solid heat conduction. So this is a heat conduction problem, subject to proper boundary conditions. This is not an easy problem because this has got a complicated geometry and all that. This is not a simple one-dimensional thing, right? But provided you can handle complicated geometry, 3 dimensions and all that, provided you can handle properties of molten metal, properties of solid metal and everything, and also build in the information on heat transfer coefficient, insulation thermal conductivity, metal thermal conductivity, etc., etc., all details, provided you can put all details, it will work. You can get a unique solution. Then that's an analysis problem. Okay. So so when in terms of the governing equations and the appropriate boundary conditions, the results are generally well defined and unique. Like in the previous problem, as I said, so this is going to be unique. Okay, so let me also tell you this. When I discuss these slides in class, don't try to read. Okay, I'll point out, like for example, I just say this one, you can just read this part. Okay, don't if you look at, if you try to read this, then this will be a distraction. Follow what I'm saying. Okay, this is more details are given because I'll share the slides with you, then that will be helpful for your study. That's the purpose. Class just depend on what I'm saying. Look at the figure, look at what I'm writing on the board. Few things I'll write on the board also. Okay, fine. So this is the analysis problem. Now so what is the design problem? Design problem is, this allows the choice of materials and dimensions of the mold wall and insulations and cooling conditions in order to reduce the solidification time below a desired value. So the desired value is there is some casting time. So that is that we are writing as tau cast. Actually, this should have been in the subscript. Okay. So tau. So you decide that okay, we want some value of tau cast. You know that the metal property that you're going to get is also going to depend on the casting time, right? Isn't it? And if you give too much a time or too short a time, then some things will happen. What will happen? The metallurgical properties, thermal stresses, those things will get affected. Right? So this is an objective. Tau cast is an objective, right? So uh, if you want to reduce the casting time below a specified value, tau cast should be less than this one. Okay. So um, we need again, if each one of you does this problem individually, then you will make various choices of materials and insulation material dimensions and all that, and you will end up with various designs. Correct? Like your design will not be the same as his design, as I have been saying. So again, this becomes a design problem, no longer an analysis problem. So this is, we just give the solidification time requirement, then we get various designs. And so this is one way of approaching the design problem. There's another way. We can say that the temperature gradients in the casting, okay, those can also be kind of specified. And then we can say that this more than this temperature gradient is not allowed in the casting. Okay, that will also give you another design. So this is, everything is now pointing towards the fact that this will be an open-ended problem. Okay, again, no unique solution. So there's not that much time today, but I will start with something else. So now, so broadly, you understand that design is different from analysis. Now, when you do design, there is other aspects also. There's some synthesis that we also need to do. Now, what is synthesis? Synthesis means, see, for example, in all the problems that we have discussed so far, we have kept a narrow focus. Okay. So the heat exchanger problem, I just said that, okay, just do this tube dimensions and duct dimensions, spacing, pitch, etc., and then just maintain some velocities, gas velocity, water velocity. This is a design. Okay, then you see an optimum design or whatever is optimum design. But in an actual case, it will not be, usually not be just a thermal design. Okay, for example, in heat exchanger design, the heat exchanger after all is a structure. So you have these tubes and then they have to be placed properly. When there is a flow, it should not shake also much. The flow should not induce vibrations in the setup. Shell and tube heat exchangers. Shell and tube heat exchanger, you have baffles. Anybody has seen that? Baffles. Okay. So these tubes with baffles, these things give you a structure. The structure has to be structurally stable also. Correct? In fact, the baffles give you some kind of structural stability. So there are structural aspects. There are manufacturing aspects. Whatever you design is not useful if it's not possible to manufacture that. Whatever you design, you cannot choose unrealistic materials. The materials which are too expensive or materials which cannot be machined to produce that product, those things cannot be done. So it's not just thermal design. It's also materials, manufacturing, okay, maybe some vibration effect, all kinds of things. Right? Everything has to be put together. So you need this aspect of synthesis also. So if you work in an industry to do heat exchangers there, so let's say that company designs heat exchangers, and then also that company manufactures heat exchangers. Okay, let's say that happens. Then you can work on the thermal design of it, but you will have your friends from solid mechanics and design and all that, mechanical design. They will also look at the structural aspects. They will also look at the stresses, right? And maybe also some vibration issues. So once you make your designs, you have to sit together and they have to put everything together and also see whether those things can be properly manufactured, whether the heat exchanger can be easily cleaned, because the heat exchanger will get fouled over a period of time. Then how to clean that? Everything has to be put together. Otherwise your design will not work. Design is not just thermal design. Okay. So that's why you need synthesis. Now synthesis, I just got this definition of synthesis from Cambridge Dictionary. So if you go to I think dictionary.cambridge.org or something. Okay, so you can get this definition. So synthesis is the act of combining different things, different ideas. So for example, there's a musician who makes this album. So this example is also from the dictionary website. So this album is a synthesis of African and Latin rhythms. Okay, maybe it can be called fusion music. I do not know so much about music, but it's basically making rhythms which has got some combinations. Okay, putting things together, that's synthesis. So we have to put these things together that we can get strength of materials, manufacturing, production, etc. to in the casting problem, for example, to get a proper design. So this is synthesis. Fine. So it's 10:55. I think we have to stop here. Now we will discuss this a little bit more in the next class, and then we also will talk about something called selection. So there is a comparison between selection and design. So we'll talk about that tomorrow. Now, much of this discussion I'm doing from this part of the discussion, lecture 2. This is from a book called written by Yogesh Jaluria. Okay, so this is there in the course introduction sheet. Course introduction sheet I distributed to people who came in the last class. I don't have that with me today, but I'll upload this on Moodle. Okay, right. So thank you.